This series of videos is going to be looking at liquid-vapor equilibrium. In these first parts, I will be deriving the equations we need for bubble point and dew point calculations. So we're going to start with the bubble point calculations. We're going to do a bubble pressure calculation at a constant temperature and a bubble temperature calculation at a constant pressure. So to start with these, we need to look at Raoult's law because we will be using it to derive these equations that we need. So Raoult's law states that the liquid mole fraction of component I times the pure component saturation vapor pressure of component I is equal to the vapor fraction of component I times the total pressure of the container. And if we think about it, the vapor mole fraction times the total pressure of the container will just give us the partial pressure of component I. And so we're going to be using this to calculate the bubble pressure and bubble temperature points at for a mixture of liquids. So I'm going to start with the bubble pressure. And this calculation is the pressure at which the first vapor bubble will form in our mixture if we hold the temperature constant. And so we'll have a container of all liquid, and there will be a piston at the top. And in order for the first drop of vapor to form, the sum of the partial pressures of the components needs to be equal to the pressure that the container is under. So we can state this by saying the sum of the partial pressures, which is given by the liquid mole fraction of the component times its pure component saturation vapor pressure, is equal to our bubble pressure. So we'll be given the liquid mole fractions. In this case, for this problem, we will have 0.3 mole percent benzene and 0.7 mole percent toluene. 0.7 mole percent toluene, and from there we can go ahead and start to plug this into our equation. So the liquid mole fraction of benzene is 0.3 times the pure component saturation vapor pressure of benzene plus the liquid mole fraction of toluene times the pure component saturation vapor pressure of toluene. And we will be able to calculate these saturation vapor pressures using Anton's equation. So it'll look something like this: log base 10 of the pure component saturation vapor pressure of our component will be equal to A plus B over C plus T. And in this situation, since we are under constant temperature, we'll be able to solve for these and then from there solve out for our bubble pressure. Now I'm going to be looking at bubble temperature, and in this case, for bubble temperature, we again have a container, but in this case it's under constant temperature, or constant pressure, and we need to find the temperature at which the first drop, or the first bubble of vapor will form. So again, we'll be using Raoult's equation and the idea that when the sum of the vapor pressures of the components in the container is equal to the pressure that is being exerted on the container, the first vapor bubble will form. And so again, we'll have that the total pressure will be equal to the sum of the vapor pressures. And in this case, we know our pressure, so we're not solving for this, but we need to solve for the temperature. So again, we'll have the mole fraction of benzene times its saturation vapor pressure plus the mole fraction of toluene times the pure component saturation vapor pressure of toluene, and that will be equal to our pressure. And so from here, again, we can use Anton's equation to find both of these, but in this case, we will be solving for this temperature instead of solving for the pressure. Since we already know the pressure, it's held constant. And so to solve for this, I'll be using root solver in the later videos in Python, and I'll also be solving for the bubble pressure. And now we are going to be moving on to the dew point calculations. So now moving on to our dew point calculations, I'm going to start with dew pressure. We are going to have a container with our 30% benzene and our 70% toluene mole fraction ratio. And this time we are going to have all vapor in our container. And it will be held at a constant temperature, and we are going to be pressing on the container until the first drop of liquid forms. And when this happens, there's going to be a mix of toluene and benzene in the drop, but the sum of those mole fractions in the drop will be 1. So this is very crucial in our dew point calculations. Without this, we really can't derive the expression, so it's crucial to remember this. So the sum of the liquid mole fraction will be equal to 1 when that first drop of vapor, or first drop of liquid forms. And so from here, we can now use Raoult's equation, which I will rewrite down here. And we know this, we know our vapor mole fractions, and so we can rearrange the equation and solve for the liquid mole fraction. So the sum of the liquid mole fraction will be equal to 1, which is equal to the sum of our vapor mole fraction times the total pressure of the container times the pure component saturation vapor pressure of each component. And then from here, I'm going to plug in values, and that'll make it a little easier to solve for the dew pressure. So I'm just going to plug them in up here. We have 1 will be equal to the vapor mole fraction of benzene times the total pressure over the pure component saturation pressure of benzene plus the mole fraction of toluene times the total pressure over the pure component saturation pressure of toluene. And then I can factor out the total pressure, which is what we'll be solving for in this case. And then from here, it's quite easy to solve for the pressure. So our equation for our dew pressure will be equal to 1 over the sum of our vapor mole fraction of each component divided by each component's saturation vapor pressure. And now for dew temperature, which I'll do over here. We have the same container with all vapor in it and our 70 to 30 mole ratio of toluene to benzene. And instead of pressing on the container until the first drop of liquid forms, we'll be holding it at a constant pressure and heating it up until the first drop of liquid forms. So we can actually use the same equation, but this time when we're doing our dew temperature calculation, we'll know the pressure, and then we just need to use root solver with Anton's equation, which will give us the pure component saturation vapor pressure, and we can use that equation to solve for T.